8M6 lesson 10, linear models. So when we work with statistics, we typically create linear models to be able to make predictions and work and want to understand how two variables relate. So we're going to learn a few terms, a few vocabulary words today, and then we're going to go through two examples of things that really use the work that we've been doing for 2 whole units now. And so that should feel like a little bit of review. So some new terms, a little bit of review, and that'll be the entire lesson. Okay, so in this lesson, we want to talk about dependent and independent variables. So dependent and independent variables, that's our 2 key vocabulary words, if you will. And then we're going to, again, do a review of 8M4, 8M5, 8M6, and we're going to connect verbal models, graphs, equations, and t-charts, stuff that you should be very familiar with doing. So let's talk about independent and dependent variables. So when we're running experiments, or we're doing science, connecting math in the real world, we often want to do things like make predictions. So we have 2 variables, types of variables. One's the independent variable and one's called a dependent variable. And pretty much the bottom line is the independent variable is the one that goes on the x-axis. So when you're looking at something like this x is the independent variable, and the y is going to be our dependent variable. That's just the convention that we use when we're writing up our experiments, or we're writing up our prediction models, or building our scatter plots. So what do we mean by a predictor? And then this is also an independent, but it's also called, you can think of it as a predictor variable, and that y is the predicted variable. So often when you're running an experiment, you want to know something, and you want to be able to predict an answer based on something. So a predicted variable might be something like how fast something goes. You want to run an experiment and figure out what makes something fast, or you want to run an experiment and you want to learn about what score on a test someone might get. And an independent, a predictor variable for how fast someone runs might be like, how old they are. And you might expect that, as the older someone gets, the faster they are. You might also say, how tall. Sometimes some people think that taller people are faster because they got longer legs. So you might want to run an experiment. You might want to figure out whether taller people in your class are faster. Does your graph look like this? Or maybe your scatter plot looks like this, in which case, it may not be a predictor. Maybe if you ran a how tall and how fast experiment, maybe it would look something like this. Maybe really tall people aren't as fast, but taller people are faster, and then shorter people are slow. I don't know. You can run that experiment yourself. However, let's say that you wanted to run run an experiment and figure out what score someone got on a test. Well, what independent predictors? Probably how tall you are. You could probably, if you said how tall someone is, to figure out what score they would get on a test, and you put tall down here, their height, I'm going to predict that you're going to get no correlation. You're going to get something kind of flat, which would have no correlation. But maybe you said how much study time. So we didn't do tall, and we said, well, you study for 1 hour, 2 hours, 3 hours. Maybe then your scatter and your scores were like 60, 70, 80. Maybe then the more you study, people who study more might get better scores. I don't know. You can run that experiment. So this is like our predictor variable, and this is our predicted variable. This is the thing we care about figuring out the answer. Over here, it is, well, what are the things that can cause that thing to be higher or lower? So let's go and start to understand more about independent and dependent variables. And maybe we'll understand them a little bit better as we should. Here. Okay, whoops. Okay, there we go. We're going to open. Okay, so now you went through an experiment or some examples like this in class. So you talked about a predictor variable, and you talked about then identifying some predicted variables. You also went through an experiment of finding some predicted variables or dependent variables, and then what things might predict it. Okay, so let's go through that. So again, I'll draw a little chart over here and remind you that this is the predicted, this is the Y, and this is also called the dependent variable. And over here is our X, which is our independent. It's also our predictor. So right now we're going to say, well, if we want to figure out what the height of a plant is, the height of a plant, and let's say we're going to make that in inches. How high can a plant grow in 3 months? Well, what are the predictor variables that might go into creating a taller or shorter plant? Well, I'm going to say how much water. How much water in, say, so I predict that maybe more is going to make a taller plant, and then the more water, if I want it might be shorter. So I'm going to predict maybe that my graph looks like that, but I don't know. I'm just going to have to go out and run an experiment where I plot data, but I need to know what to put on the X and Y axis. So this might be a good idea for a science fair experiment. Also, what else might affect the height of a plant? Well, fertilizer, the amount of fertilizer. And that can be also measured in ounces or maybe grams. I don't know. Okay, let's look at a different question now. Now my question is going to be, what I measure the height, or I want to measure the speed of a derby car. So I want you to think about it. I want you to pause and think about B, C, and D. Pause, think, and write. What are some things that could change the speed of a derby car? One of those, those cars that you race down a track. The Boy Scouts do this every year. They get these cars, track, and we try and figure out, they try and make ones that are fast. What are the things that can affect the speed of a derby car? And that would be a predictor variable. The percent of kids liking cake. This might be, well, think about the kinds of things that might affect how many kids like a cake. Like if I put out different cakes, what things could affect it? And how about ice cream cones sold? This is a different predicted variable. What things could affect how many ice cream cones I might sell on a given day? Okay, now I assume you've paused and thought about it and that you've come back. So let's think. Let's talk about the speed of a derby car. Well, some of you might have said something like the weight. Maybe the weight of the car affects it. Maybe. And we'd measure that in, grams or ounces. Either one. Also, how about the size of the wheels? That might be one. You might have had some other ones. Size of the wheels in, inches. Okay, percent of kids liking cake. Well, I might say, what type of cake? It might be like chocolate. We might have chocolate. Vanilla, strawberry. So just a type of cake. What else? They might like. Is it the sweetness? I mean, I don't know. I'm making this up. How much sugar and grams go into the cake? So you could make a bunch of different, to measure it, you could make some different cakes with different amounts of sweetness in it, different cups of sugar, and then see if they like the ones without any sugar, the ones with too much sugar, and maybe there's a happy medium. All right, ice creams sold. This could measure that in, say, Fahrenheit. Ice cream, so you could also say location, maybe. You know, I could sell it in, you know, the city, or in the, you know, in the neighborhood. So these don't, so notice how these predictor variables can sometimes be things that are measured, they're continuous, like ounces. I could measure that 0, 0.1, 0.2, 0.3. I could, a number that's on a continuous scale, or I can sometimes have predictor variables that are just very finite things. They're like, you know, 5 locations, and so you only get 5 data points. Okay. All right, now let's switch gears a little bit and let's talk about predictor variables and what things that they might predict. Okay, so now we're not talking about trying to guess at what things I'm trying to measure. Now we're going to start with things that are independent, and let's figure out what things they could affect. So like the amount of money in my pocket, what could that affect? So I want you to pause and try these 4 things. Okay, now we're back. Now let's go through this one at a time. So the amount of money in my pocket might affect the, you know, the candy, the amount of candy I buy. The amount of money in my pocket might, you know, affect, you know, how long I stay. If I'm, say, at the fair and rides cost a certain amount. Okay, an age of a person. Let's see. These are just some things that it could. I mean, these are. I mean, I'm just there's a million different answers. I'm just coming up with 2 of them so you can understand. The age of a person might affect how fast they are. You know, we can make a scatter plot. The age may, you know, you maybe get faster and then you may get slower. You know, old people may not be as fast as kids who are, you know, 20. You know, this might be 20 might be the fastest you get, and after you're 20 you get slower. Maybe it's 30, but I predict that probably the younger kids are slower, and then the older people are slower as well. They're fast. How fast? Speed. Speed. Okay. Also, the age of the person might be your salary. The older you get, you might make more money at your job, salary in dollars. Type of battery. What could that predict? Let's see. Type of battery, you know, different types of batteries. This is like, you know, C, D, AA, AAA batteries. The type, it might predict how long they last. How long they last. And you might measure that in hours. The type of battery, let's see, what else? It might, you're sold. Right? It might be the certain types certainly sell more than other types, and you might run an experiment. What types of batteries sell more and sell worse? Okay, let's see. Predictor variable, number of Instagram posts. Well, let's see. The more posts, it may give you more replies, the number of replies. I don't know. Maybe you can think of some other examples of some predicted dependent variables. So hopefully we get a sense of this. Predicted, independent variables, predictor, independent, predicted, independent. Hopefully we got a better sense of what goes on a y-axis when you're doing scatter plots with statistics and what goes on the x-axis, which are these independent and predictor variables. Okay, let's go forward. And now we're going to start talking about some linear models. And we've been doing this, but your homework is going to be to do 3 types of problems like this. So you go to the fair. You are at the fair. And rides cost $4 each, and entry costs $10 to the fair. So you pay $10 to get in, and then $4 each ride. So it's $4, what can we say? $4 per ride. And what does that, this per thing, that's a code word. What does that mean? So we're going to make a T-chart for 0, 5, and 8 rides. You're going to graph the data over here, and then you're going to write the equation of the data. So I'm going to let you pause and try. So I want you now to pause and try. Now I assume you're back. So let's make our T-chart. Remember, we starting with the verbal model. This is a verbal model. So our verbal model, our T-chart, our graph, and our equation, all the same thing. So over here, let's make our T-chart. This is our number of rides. This is our X. And Y is going to be our what? It's going to be our dollars, our cost. Okay, so let's make a T-chart. 0, 5, and 8. Well, if I go on 0 rides, I still have to pay to get into the fair, so that's 10. If I go on 5 rides, that costs me 4 times 5 is 20, plus the 10 to get in, so that's 30. And then if I go on 8 rides, that's 8 times 4 is 32, plus 10, 42. Let's see, so we need to graph this. So let's see, if I want to fit 42 on here, well, this is going to have to be 10, 20, 30, 40, 50. Any other scale is really not going to be very good. Probably. Maybe you came up with a better scale. Maybe you made that 8, and this was, every one was 2. So that maybe that was 8, 16, 24. I don't know. But this is a pretty good scale. And so let's see, number of rides. Well, let's see. I can't make those 1. I have to make this 0, 2, 4, 6, 8. Yeah, that'll fit nicely. And so this is our X, and so this is the number of rides. So we're going to graph our data. 0, 10, 5, 30, and 8, 42. Make our nice line. And we're done with our graph. So let's see. 6 rides would cost about, 30, 34. But we can figure that out by making the T-chart. Remember, graphs aren't perfect predictors, but they can get us pretty close. 10 rides should cost us about $50. Right? Good. So we've graphed our data. We've made our T-chart. Check, 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 check. So we're going to write the equation of the data. Now we can do this using any of our 3 things. We could make it from our graph. We could find our M and then our B and make it from our graph. We could make it from our T-chart by finding delta Y over delta X. Let's do it. Let's do that. Let's do it from the T-chart. And then we'll do it also from our verbal model. So here we have delta Y over delta X. And in this case, let's use these points here. So our delta Y is equal to what? Plus 20. And our delta X is plus 5. This is plus 5, and this is plus 20. So that's 4. And our y-intercept, and so that's our m. And our y-intercept is where x is 0, y is 10. So our b is equal to 10. So our equation is y equals 4x plus 10, where y is in dollars and x is the number of rides. Remember how to do that? Hopefully we do. Hopefully we are solid at that. That's going to come back to us in high school and in Algebra 2 and in our SATs and all kinds of tests in the future. Now, we could have done it just straight from our verbal model. We could have written the equation, right? $4 per ride. Kent, this is our slope. M equals 4. And B, our starting point, is 10, right? 0 rides would cost us $10. So we can see our y-intercept of 10. So we could have used these numbers right here to make the equation. Finally, from the graph, we could have made the equation. We know that this is our y-intercept. Our y-intercept equals 10. And then our slope we could have calculated from any 2 points. So let's look at this. Let's take these 2 points here and do our rise over our run. Our rise equals 20, and our run equals 5. We went from 0 to 5. So our rise over our run equals 20 over 5 equals 4. So that's our slope. So we could have done it from here, and then we could have come up with this same equation. Nice how it all fits together. So that deserves how many happy cats? Well, we got to get our happy cat. Somehow it always goes back to happy cow. So we're going to do happy cat for our graph. Happy cat for our t-chart. Happy cat for our equation. And just a general happy cat for a general understanding of how all of those hook together. Let's do one more example and then we'll be done. So this is actually an example that's maybe even a little bit simpler, but we're going to do it because it's kind of like the one in your homework, in one of your homework questions today. So Abby runs 7 miles per hour. Bill runs 6 miles per hour, and they run for 3 hours. They both run, and they run at a constant speed, which is almost impossible, but let's just say that they do it for the sake of the model. So we're going to graph their distances as a function of time. Well, one easy way to do this is just to make a t-chart and then graph it. So let's do that. This is homework help. And so I want you to pause plus graph using t-chart. Or other method, if you want. I'm going to use a t-chart because it's really pretty straightforward. There's other ways to do it. Okay, I assume you've paused and tried. So let's do Abby, and we'll do Abby in light blue. Abby. So after hours, and then her distance in miles. So let's just do it for 0, 1, 2, and 3, because she ran for 3 hours. After 0 hours, she's run 0. After 1 hour, if she goes 7 miles per hour, how far has she gone in 1 hour? Well, she's gone 7. And then after, she's running at a constant speed. So after 2, she's run another 7. And after 3, she's run another 7. So if we graphed her distance, well, now we got to figure out, well, let's do Bill real quick. Bill will be in orange, and in his hours and his mileage. After 0 hours, he's gone 0. After 1, if he goes 6 miles every hour, after an hour, he's gone 6. After 2, he's gone 12, and after 3, he's gone 18. So Bill, so now we need to put our scale out there. Let's see, 0, 1, and 3. So we could go 0, 1, 2, 3. That'll fit nicely. And then our distance, we have to be able to make sure we fit 21 on here. So so this could be 5, 10, 50. Oh, this is going to work nice. 20, 10, 5, 15. So 21 is right here. So Abby's gone 1. She's gone. Let's do her color. 1, she's gone 7. After 2, she's gone 14. And after 3, she's gone 21. Okay, and then Bill has gone, and she hasn't gone any further. I don't draw a line here, an arrow, because we're only running for 3 miles, so we stop there. So Bill has gone, whoops. Let's make his points first. So Bill has gone 0 after 0. After 1 mile, he's gone 6. After 2 miles, he's gone 12. And after 3 miles, he's gone 18. A little bit below. And so that's Bill's line. And so what can we see? We can see that Abby at any point in time is always a little bit ahead. So if we look at 2.5 hours, she's ahead. She'll always be ahead of Bill if she runs a constant speed and runs faster. She's always, after 3 hours, she's 3 miles ahead. After 2 miles, she's 2 hours, she's 2 miles ahead. After 1 hour, she's 1 mile ahead. So a lot of stories can be told by this graph, but very easy to graph if we use for this particular story. So let's lay down some happy cats for that. For the T-charts and for the graph. And you have a question that's kind of like this one on the homework, and it should be pretty straightforward given everything that we've done over the last several months. Okay, we're going to call that good for the day. And we're going to sign out here and say that was lesson 10. That was 8M6 lesson 10 linear models. And we're going to continue to build on these linear models and for 4 more lessons, and then we're done for the year before you head into AM1, which is algebra module 1. Well, you've been doing algebra for all year, but you're going to go to the official high school algebra class after 4 more lessons. So well done. Keep up the great work. Hang on through the end of the year. And we'll be seeing you next time with lesson 11.